Let's denote an encryption of a message W with a public key PK and using random padding R by EPK of W semicolon R. Okay, so R is not part of the message, not to be confused. R is the random padding, W is the message. That's how I'm going to denote it. And now what's important to note is that if I'm given a public key and I'm given a ciphertext and a plain text and the random padding, I'm basically given everything which I did to encrypt, then it's possible to check what is encrypted in that ciphertext. I don't need the secret key. All I need to do is just follow the procedure again, re-encrypt by following and doing exactly what the server did by an ambiguity of encryption, and it's a little bit technical, but it's not difficult to show. This ciphertext cannot be an encryption of anything else, and so the server cannot trick me. It can't give me some wrong random padding and somehow convince me of something which isn't true. A ciphertext locks the message inside because otherwise we wouldn't necessarily always decrypt correctly. So now we have a proof of equality. All the server needs to do is show me what it did to encrypt. Well, now we have a problem of how to use it. Because when can the server send me this proof of equality? If it sends it to me before I've decrypted, before I answer with W, then what's the problem? I'll know W even if I'm not authorized. Right? If it sends me all the information that it used to encrypt, then obviously I'll be able to learn W, and even if I'm not authorized. So that doesn't work. And if it sends me the proof of equality afterwards, then it may already have learned my identity. Because if it cheated and encrypted different values, then it's going to know who I am. But this is where verifiable anonymity comes in. What I'm going to do is I'm going to return W, but then I'm not going to proceed until the server convinces me and shows me that everything that it did is okay. So let's have a look at the full protocol. The user sends an authentication request. The server chooses a long random string W and encrypts that string, that same string under all public keys. It may cheat. That's what it's supposed to do. Okay? But it may cheat. I'm not saying it can't. The user decrypts the ith ciphertext because that's the only one it knows how to decrypt and sends back the value W. And the server then accepts the user and allows it access as long as it sent back the right string. But then it sends all of the random blocks that it used to encrypt those L ciphertexts. And the user just verifies that all of the ciphertexts that it got originally are actually encryptions of the same string W. And that's your proof that you asked about before. How can I check that the server is really acting correctly? This is exactly how I check it. And notice that it gives me exactly the verifiable anonymity that I talked about because I'm not going to proceed to the next stage until I get those R1 to RL and check really that I'm safe. Yes?
So why can't it send R before receiving correct W?
Okay, so the reason is that if it does do that, then you have no guarantee of security of the encryption. Encryption is... Yeah. And in fact, there are a lot of attacks. There was a previous paper that tried to do that where they said, we'll just encrypt W without random padding. But then it said, well, the only problem is we don't really know what encryption scheme to use because RSA is a problem. We know of RSA attacks if you encrypt the same message under many public keys. It's not a known plaintext attack. It's just a ciphertext attack. Given the public key, if you encrypt the same message under many public keys in RSA, then you can get back that message. So you have to have random padding, and once you have to have random padding, then if you give up the random padding, then you've lost at least your guarantees. We have no knowledge of how to prove that it's fine, and it probably isn't. So I have this theorem that says that if the encryption scheme is secure under chosen plaintext attacks, the most basic level of security for public key encryption, then the protocol is secure. For anyone who really wants to see actually a full cryptographic proof of security, it's in the paper in the CD, but I've put it in an appendix so as not to scare other people off. The basic idea is what I mentioned. It's secure authentication because only a legitimate user is able to decrypt one of the ciphertexts, so only a legitimate user can return W. And it gives anonymity because if this user does not get cheat, then it knows that all of the ciphertexts encrypt the same W, so it knows that the server has no way of knowing who it is. Again, all of the users will behave in exactly the same way, so there's no way of detecting that it's me and not someone else. What's the efficiency of this protocol? And here we get to more tricky issues. Well, the server overhead is a single encryption per user with RSA and a small public exponent that's not too expensive, depending on what L is. And I'll get to that soon. The client overhead is also to compute one encryption per user. That's for the check at the end. It has to re-encrypt, so it has to carry out that re-encryption. And one decryption. What's important about this solution is it uses only one decryption, and if we're talking about PKI and public key technologies, we'd like that decryption to be on a smart card, but it's only a single decryption. And one of the important things about this protocol, and this is when I started looking at anonymous authentication, this was really my goal, there are a lot of papers out there in the cryptographic world on anonymous authentication or anonymous credentials in general, and they have lots of nice features and lots of nice properties, but they all use very, very special purpose number theoretic problems and algorithms. The problem with such solutions is that if you want to actually deploy them, you can't use standard certificates. You need some different type of digital certificate, at least not one that you buy for RSA signatures or RSA encryption, because it's using something based on something completely different. And you also can't use standard smart cards, because standard smart cards do RSA and possibly some other things, but nothing that's being done in the anonymous credentials and anonymous authentication work until now. And this protocol allows you to use a standard PKI. So I already have a smart card. I already have a digital certificate for my smart card logon at work. Once I already have that, that's all I need to be able to, at least on an infrastructure level, to be able to run the protocol. And that I think is very, very important. If we're going to come up with cryptographic solutions to problems, we need to have them be easily deployed on an infrastructure level. In theory, there's no problem. There's no difference between RSA and between the bilinear Diffie-Hellman assumption, if anyone's aware of it. There's no difference on the theoretical level, but in the practical level, there's a huge difference, because I have an infrastructure for one, and I don't have an infrastructure for the other. But what about large or very large sets of users? Okay. If we're talking about thousands of users, then it's impossible, or it's not impossible, it's infeasible to expect a server to carry out thousands of encryptions per authentication. If you think about the user, it's actually not an issue, because it's not a big deal for the user to encrypt 1,000 times on a PC. If you think about the algorithms for encryption, decryption, RSA at least, 1,000 encryptions on the PC would probably take no more time than one decryption on a smart card. In fact, it could possibly even be less if you're using small exponents, small public exponents. So in terms of scalability, it's a problem on the server side. But we can use something which is called k-anonymity. And k-anonymity means it's something which is used a lot in the privacy world. And it tells you that I can release information, I can release databases, as long as it's guaranteed that I may be able to locate a user, but only within a set of k others. So no one can know exactly which record in the database refers to me, but they can know that I'm one of these k records. In general, actually, I don't like k-anonymity, because it may be that you can only know that I'm one of the 100 database entries, but it may be that all of those 100 database entries have AIDS, and so it doesn't really help me that you don't know which one I am. Whereas what I'm talking about is a high level of k-anonymity, where I say that you can't locate me within 100 random users in that database. And that's a much, much stronger guarantee. And the way to achieve this is, rather than use all of the users when I'm authenticating, I'll choose a random subset of, say, size 100. In fact, smaller would even possibly be reasonable. That's something which is already more of a policy level than a technical level. But I'll choose a set of users, and I'll hide within that set of users, of 100 users, and that would suffice. So you wouldn't be able to link me because of that. An implementation issue that arises then again is, well, the protocol, as I mentioned, assumes that all the users know the other user's public keys. That assumption is implicit in that I have to re-encrypt. And if I have to re-encrypt, I have to know the other user's public keys. And the question is, how is this accomplished? Because let's think of the following malicious server. If the server is going to post all of the public keys of the users, then it can actually post 90% of them to be fake. And when I choose my random subset of 100, maybe I'm really choosing 90 fake and only 10 real. So that's an issue, and that's an issue that has to be solved. You would need to have some external source, or to have a fixed set of users ahead of time that you're going to decide to be together and keep your anonymity at that level. What about full anonymity? What I gave you until now was the protocol for verifiable anonymity, which said that the server may be able to cheat, but then I'll detect it. What happens if you want to prevent all cheating? And here is a very nice trick, which is based on something called ring signatures. Ring signatures is a new primitive which was proposed by Rivest, Shamir, and Talman. It's the same Rivest and Shamir as in RSA, but Talman is, Yael Talman was a master's student of Adi Shamir, who did this in her master's thesis. And it's a way of signing on a message so that you have this ad hoc ring of users, and you sign on the message so that only one of the users in the ring, it's really just a set of users, could have signed on the message. But it's impossible for anyone verifying to know which user it was. Okay, so it sounds very similar to what we're doing. Interesting, the rings can be formed by anyone on their own, and this is an interesting twist. The initial application they suggested this for was how to leak a secret. What does that mean? Let's say I'm a member of Congress, and I want to leak something secret from the government to the press, but I want the press to be sure. I want to convince the press that I really am a member of Congress, and I don't want to let them know exactly who I am because then I'll be in trouble. So what I can do is form a ring of all the users, all of the members of Congress with their public keys, their RSA keys, and I can sign on that message without even needing the consent of those other users. So when Adi Shamir presented this at the crypto conference, someone got up in the audience afterwards and said, if you ever wanted to give me a good reason why not to use RSA, that's it. Because basically what that means is that anybody here who has an RSA public key, I can sign on something that's everybody in the world will know it's either me or you. And there's nothing you can do about it, and you'll automatically become suspect. So that's the initial application that they were thinking of for ring signatures. But I'm going to use it for something different. It uses, again, you can use regular RSA. It requires one decryption and an additional encryption for the rest of the users. So it's the same complexity as in my previous protocol. And just to get a feeling of how it works, the basic idea is, let's say you have 6 users, then in order to sign on a message, you have to close the ring. The way you can close the ring is only one way. You can go forward 5 steps, but you can't close it by going forward a 6th step. In order to close the ring, you have to go backwards. In order to go backwards, you need to know the secret key. It doesn't say anything. It's actually quite a complex solution, but just sort of to give some sort of feeling how it works. And this can actually give anonymous authentication in a very, very nice way. You can incorporate it into SSL very, very directly. SSL with client authentication, for those of you familiar, works by having the client sign with a digital signature on all of the handshake messages until that point. That's the way client authentication works. So all you need to do to get anonymous authentication is just use a ring signature instead of a regular signature. That's the only difference.